Okay, so we are on day 2 of our topic 1 notes, and as promised, I'm going to give you a little more detail about Newton's second law. So the first thing is this idea that a force will make an object change speed and direction. Now, a couple of things about that. A change in speed okay, a change in speed, that is an acceleration, if you remember that from before. So acceleration is involved here. The other thing that's involved here, right, is this idea of a change in direction. Change in direction can also mean acceleration. Okay, so we have either a change in speed or a change in direction. In fact, let's fix this right here and let's add an or, because it can be both or it can be one of them. So we have an acceleration involved, and so a force will cause an object to accelerate. Because of inertia, an object with more mass would require more force to get the same acceleration as an object with a similar mass. So if you remember this idea of inertia from Newton's first law, law of inertia, let's just kind of remind ourselves about it. So inertia, remember we let I represent inertia. If inertia increases or is increased, that means that the mass is large, okay? And if inertia was decreased, that means that the mass was small, okay? So we can have a direct relationship with force here. The force of an object, because it equals mass times acceleration, if I increase the mass, and I keep acceleration constant, then my force will increase. And then the same thing's true if I decrease the mass. So if my mass is small, and we keep acceleration constant, then my force will decrease. We call that a direct relationship. All right, now there's a scenario where you have a car. Okay, so here's your car, and your car is driving down the highway, and it is cruising at, let's say, 65 miles per hour. And a poor little old butterfly, this beautiful old butterfly here, decides to take a trip to the other side of the highway against his parents' will, and ends up colliding, or the car, I should say, collides with the butterfly. And so what we get is we get a mess on our windshields, right? And you guys know this happens anytime you travel during the summertime, springtime, fall time when the bugs are out. If you look at your windshield afterwards, you got a bunch of little buggy bugs all over the place, mosquitoes and gnats and things like that. But what is interesting about this story is that the force that the car applies to the bug, so we'll represent that with this yellow arrow, the force of the car on the bug, right here, so we'll say car, for C for car, is actually the same amount the same amount as the force that the bug hits the windshield with. Okay? And I'm going to use Newton's second law to explain that. So we're going to use a B for bug. So we would say that this F sub C, force of the car, is equal in magnitude. Now the way we represent magnitude, this is going to be kind of new for you guys if you're not in, like we'll say calculus, is this absolute value symbol. That means magnitude. It means we're worried about just the amount, not the direction. Okay, is equal to the magnitude of the bug on the windshield. Now you're thinking to yourself, well, how can that be? Because the bug is so little and the car is so big. And you're exactly right. How can that be? Well, the mass of the car is huge, right? So what we're going to do is we're going to use this big M to represent the huge mass of the car. But the acceleration of the car when the bug hits it doesn't really change direction much. In fact, your windshield, if you were to be able to zoom in almost microscopically on your windshield to see what the molecules are doing on a molecular level, you would notice that the windshield actually will bend a little when the bug hits it. Now, it doesn't change direction drastically. In fact, when you hit a bug on the highway, you never really notice it or feel it. But your windshield actually does experience an acceleration. It is teeny tiny. So you have the force of your car, the windshield, hitting the bug, represented here with the yellow. And then take a look at what happens with the bug's force. So I just told you that the bug is going to hit that windshield with the same force. Well, the bug, oopsies, the bug is really, really small. Okay, so we're going to use a little tiny m to represent the bug, really small mass. But 1 second it's going one direction, the next second it's going with your car. So it experiences a very large, we use a little a, very large acceleration. Because the mass, the inertia of the car is so large, but the acceleration of the bug is so large, they end up actually balancing each other out. And so these two equations end up being equal. Oops. And that kind of explains, that's Newton's second and third law kind of all together. For every force, there's an equal and opposite force. It's true, the bug hitting the car and the car hitting the bug, they're exactly the same force, magnitude, just opposite directions. And Newton's second law helps us explain that. So there you have it. You have Newton's second law, F equals ma. And the lab that you did in class would have done a nice job explaining that to you. Please make sure that you write down any questions that you have from this slide, and we'll talk about it in class.